Hello everyone. Today we are going to find the fixed end moments in this fixed beam using column analogy method. In this fixed beam, we have a point load W in the center. Now let us find the degree of static indeterminacy in this beam. In this beam, the number of unknown reactions and moments are 4. They are the moments MA and MB, the reactions RA and RB. The available equilibrium equations are 2. The degree of static indeterminacy is equal to 4 minus 2. We will get 2. To make this beam statically determinate, from these 4, we have to remove any 2. Let us remove MA and MB. When we remove MA and MB, this beam becomes a simply supported beam. You can see that I have converted the fixed beam into a simply supported beam. Now let us draw the bending moment diagram for this simply supported beam. We know that in the points A and B, the bending moment will be 0. And we know that in the simply supported beam, if the point load is acting in the center, the maximum bending moment occurs in the center and it is WL upon 4. We have drawn the bending moment diagram for the simply supported beam. Now we have to convert that into a conjugate beam. In this case, we have to divide the bending moment by EI. Let us name this diagram as MS diagram. Now let us make an imaginary analogous column. Analogous column is a very short column. In this column, P is the resultant load due to the conjugate beam. The cross section of the analogous column is 1 upon EI cross L. The formula to find the stress at the base of this column is P upon A plus or minus PE XA upon IY. In this formula, P is the resultant load, A is the area of the cross section of the analogous column, IY is the moment of inertia, XA is the distance from the center up to the point A. It should be L by 2. To find the stress in the point A, we have to consider positive. To find the stress in the point B, in the formula, we have to consider the negative. In this formula, E is eccentricity. We know that it is a symmetrical diagram. So, in the analogous column, the resultant occurs in the center. If the resultant occurs in the center, eccentricity will be 0. So, these two terms will be eliminated. MIA and MIB will be same. That is the resultant load upon area. Now let us find the resultant load P. For that we have to find the area of this diagram. We know that this is a triangle. We know the formula for the area of a triangle, half into BH. Here the breadth is L and the height is WL upon 4EI. Let us apply both of them. L into L, it will be L square. 2 into 4, it will be 8. So for P, we have got WL square upon 8EI. Now let us find the area of the cross section of the analogous column. It is a rectangle. The area is L into 1 upon EI. So we will get L upon EI. We know that MIA and MIB will be same. That is P upon A. We have found P and A. Let us apply both of them. Let us take L upon EI inversely and then multiply. We can eliminate L and square. Also we can eliminate EI. Finally for MIA and MIB we are getting WL upon 8. Now let us find the stresses MSA and MSB. For that we have to look at the MS diagram. In the point A, the stress is 0, and in the point B also it is 0. So for MSA and MSB, we are getting 0. We have found MIA, MIB, MSA and MSB. The formula to find the fixed end moment in the point A is MSA minus MIA. Let us apply both of them. Finally, for MA, we are getting minus WL upon 8. Similarly, to find the fixed end moment in the point B, the formula is MSB minus MIB. Let us apply both of them. Finally, for MB, we are getting minus WL upon 8. For MA and MB, we have got negative values. That means both of them are hogging. MA will be acting in the anti-clockwise direction and MB will be acting in the clockwise direction. Alternatively, we can find MA and MB by releasing MB and RB. You can see that from the point B, I have removed the moment MB and the vertical reaction RB. So the point B becomes a free end. Before it was a fixed beam, but now it is a cantilever beam. Now let us draw the bending moment diagram. From the point B, we are going to find the bending moment values. In this case, we have to use left-hand side rule. Clockwise will be negative and anti-clockwise will be positive. In the point B and under the point load, the bending moment will be 0. Let us find the bending moment in the point A. The load W is acting in the clockwise direction, so that it will be negative, and the distance is L by 2. W into L by 2, we will get WL upon 2. We know that it is negative, so we have to make the diagram below the line. Now let us find the centroidal distance of this bending moment diagram. Let us take this triangle. For this triangle, the centroid distance towards the left is 1 by 3 into B. Here the breadth is L by 2. So 1 by 3 into L by 2, we will get L by 6. And the centroid distance towards the right is 2 by 3 into breadth. Here the breadth is L by 2. So 2 by 3 into L by 2. We can eliminate these 2. So we will get L upon 3. But in this analysis, we have to only consider the centroidal distance towards the point A. So no need to consider this. Now let us make the conjugate beam. We know that in the conjugate beam, we have to divide the moment by EI. We know that this bending moment is negative. So the pressure will be acting upwards. You can see that all of the arrows I have made is acting upwards. Now let us make the analogous column. We know that the cross section of the analogous column is 1 upon EI cross L. Here the resultant P is not in the center. It is at a distance of L by 6 from the point A. We know the formula to find the stress at the base. We have already seen this formula. Let us find the resultant load P. For that, we have to find area of this diagram. We know that it is a triangle. The area formula of the triangle is half into BH. Here, the breadth is L by 2 and the height is WL upon 2 EI. We know that finally EI will be eliminated. So, for our convenience, no need to consider EI. We know that it is a negative bending moment, so the area will be negative. So for P, we will get minus WL square upon 8. Now let us find the cross-sectional area. In this rectangle, the area is 1 upon EI into L, but we are not considering EI, so 1 into L. Finally, for the area, we will get L. Now let us find the moment of inertia. We know the formula for the moment of inertia in the rectangle BD cube upon 12. Here the breadth is 1 and the depth is L. So 1 into L cube upon 12. Finally, we will get L cube upon 12. Let us find XA. XA is the distance between the center and the point A. This distance is L by 2. Now we are going to find the eccentricity. In this analogous column, we know the center. It is at the distance of L by 2. This is the eccentricity. We know that this distance, that is L by 6. To find the eccentricity, we have to subtract L by 6 by L by 2. When we do that, we will get L upon 3. In this formula, let us apply the values of P, area, IY, XA and E. Plus into negative, it will become negative. Negative into negative, it will become positive. We can take L inversely and then multiply. Similarly, we can take L cube upon 12 inversely and then multiply. After simplifying this equation, we will get this. Let us find MIA. For that, we have to take the negative sign in the formula. When we add these two, we will get minus 3WL upon 8. Let us find MIB. For that, we have to take the positive sign in the formula. When we add these two, we will get WL upon 8. We have found MIA and MIB. Now let us find MSA and MSB. For that, we have to look at the MS diagram. Let us find MSA. In the point A, we have the stress WL upon 2. We know that it is negative. Let us find MSB. In the point B, the stress is 0. Let us find the fixed end moment in the point A. The formula is MSA minus MIA. We have found MSA and MIA. Let us apply both of them. Negative into negative, it will be positive. Minus WL upon 2 plus 3WL upon 8. We will get minus WL upon 8. Now let us find the fixed end moment in the point B, MB. The formula is MSB minus MIB. We have found MIB and MSB. Let us apply both of them. Finally, for MB, we are getting minus WL upon 8. So for MA and MB, we have got minus WL upon 8. Now we are going to end this session. Thank you for watching this video.